This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. This reading by Kara Schallenberg, www.kray.org. The Origin of Species by Means of Natural Selection, or The Preservation of Favoured Races in the Struggle for Life. 6th London edition, by Charles Darwin. Chapter number 2. Variation under Nature. Contents of this chapter include variability, individual differences, doubtful species, wide-ranging, much diffused, and common species vary most. Species of the larger genera in each country vary more frequently than the species of the smaller genera. Many of the species of the larger genera resemble varieties in being very closely, but unequally related to each other, and in having restricted ranges. Before applying the principles arrived at in the last chapter to organic beings in a state of nature, we must briefly discuss whether these latter are subject to any variation. To treat this subject properly, a long catalogue of dry facts ought to be given, but these I shall reserve for a future work. Nor shall I here discuss the various definitions which have been given of the term species. No one definition has satisfied all naturalists. Yet every naturalist knows vaguely what he means when he speaks of a species. Generally, the term includes the unknown element of a distinct act of creation. The term variety is almost equally difficult to define, but here community of descent is almost universally implied, though it can rarely be proved. We have also what are called monstrosities, but they graduate into varieties. By a monstrosity I presume is meant some considerable deviation of structure, generally injurious, or not useful to the species. Some authors use the term variation in a technical sense, as implying a modification directly due to the physical conditions of life. And variations in this sense are supposed not to be inherited, but who can say that the dwarfed condition of shells in the brackish waters of the Baltic, or dwarfed plants on alpine summits, or the thicker fur of an animal from far northwards, would not in some cases be inherited for at least a few generations? And in this case I presume that the form would be called a variety. It may be doubted whether sudden and considerable deviations of structure, such as we occasionally see in our domestic productions, more especially with plants, are ever permanently propagated in a state of nature. Almost every part of every organic being is so beautifully related to its complex conditions of life, that it seems as improbable that any part should have been suddenly produced perfect, as that a complex machine should have been invented by man in a perfect state. Under domestication, monstrosities sometimes occur which resemble normal structures in widely different animals. Thus pigs have occasionally been born with a sort of proboscis, and if any wild species of the same genus had naturally possessed a proboscis, it might have been argued that this had appeared as a monstrosity. But I have as yet failed to find, after diligent search, cases of monstrosities resembling normal structures in nearly allied forms, and these alone bear on the question. If monstrous forms of this kind ever do appear in a state of nature, and are capable of reproduction, which is not always the case, as they occur rarely and singly, their preservation would depend on unusually favourable circumstances. They would, also, during the first and succeeding generations, cross with the ordinary form, and thus their abnormal character would almost inevitably be lost. but I shall have to return in a future chapter to the preservation and perpetuation of single or occasional variations. Individual differences. The many slight differences which appear in the offspring from the same parents, or which it may be presumed have thus arisen from being observed in the individuals of the same species inhabiting the same confined locality, may be called individual differences. No one supposes that all the individuals of the same species are cast in the same actual mould. These individual differences are of the highest importance for us, for they are often inherited, as must be familiar to everyone, and they thus afford materials for natural selection to act on and accumulate, in the same manner as man accumulates in any given direction individual differences in his domesticated productions. These individual differences generally affect what naturalists consider unimportant parts, but I could show, by a long catalogue of facts, that parts which must be called important, whether viewed under a physiological or classificatory point of view, sometimes vary in the individuals of the same species. I am convinced that the most experienced naturalist would be surprised at the number of the cases of variability, even in important parts of structure, which he could collect on good authority, as I have collected, during a course of years. It should be remembered that systematists are far from being pleased at finding variability in important characters, and that there are not many men who will laboriously examine internal and important organs, and compare them in many specimens of the same species. It would never have been expected that the branching of the main nerves close to the great central ganglion of an insect would have been variable in the same species. It might have been thought that changes of this nature could have been effected only by slow degrees. Yet Sir J. Lubbock has shown a degree of variability in these main nerves in Coccus, which may almost be compared to the irregular branching of the stem of a tree. This philosophical naturalist, I may add, has also shown that the muscles in the larvae of certain insects are far from uniform. Authors sometimes argue in a circle when they state that important organs never vary, for these same authors practically rank those parts as important, as some few naturalists have honestly confessed, which do not vary, and under this point of view no instance will ever be found of an important part varying, but under any other point of view many instances assuredly can be given. There is one point connected with individual differences which is extremely perplexing. I refer to those genera which have been called protean or polymorphic, in which species present an inordinate amount of variation. With respect to many of these forms, hardly two naturalists agree whether to rank them as species or as varieties. We may instance rubus, rosa, and hieracium among plants, several genera of insects, and of brachiopod shells. In most polymorphic genera some of the species have fixed and definite characters. Genera which are polymorphic in one country seem to be, with a few exceptions, polymorphic in other countries, and, likewise, judging from brachiopod shells, at former periods of time. These facts are very perplexing, for they seem to show that this kind of variability is independent of the conditions of life. I am inclined to suspect that we see, at least in some of these polymorphic genera, variations which are of no service or disservice to the species, and which consequently have not been seized on and rendered definite by natural selection, as hereafter to be explained. Individuals of the same species often present, as is known to every one, great differences of structure, independently of variation, as in the two sexes of various animals, in the 2 or 3 castes of sterile females or workers among insects, and in the immature and larval states of many of the lower animals. There are, also, cases of dimorphism and trimorphism, both with animals and plants. Thus Mr. Wallace, who has lately called attention to the subject, has shown that the females of certain species of butterflies, in the Malayan archipelago, regularly appear under 2 or even 3 conspicuously distinct forms, not connected by intermediate varieties. Fritz Müller has described analogous, but more extraordinary cases with the males of certain Brazilian crustaceans. Thus the male of a Tanais regularly occurs under 2 distinct forms. One of these has strong and differently shaped pincers, and the other has antennae much more abundantly furnished with smelling hairs. Although in most of these cases the 2 or 3 forms, both with animals and plants, are not now connected by intermediate gradations, it is possible that they were once thus connected. Mr. Wallace, for instance, describes a certain butterfly which presents in the same island a great range of varieties connected by intermediate links, and the extreme links of the chain closely resemble the 2 forms of an allied dimorphic species inhabiting another part of the Malay archipelago. Thus also with ants, the several worker castes are generally quite distinct, but in some cases, as we shall hereafter see, the castes are connected together by finely graduated varieties. So it is, as I have myself observed, with some dimorphic plants. It certainly at first appears a highly remarkable fact that the same female butterfly should have the power of producing at the same time 3 distinct female forms and a male, and that an hermaphrodite plant should produce from the same seed capsule 3 distinct hermaphrodite forms, bearing 3 different kinds of females and 3 or even 6 different kinds of males. Nevertheless, these cases are only exaggerations of the common fact that the female produces offspring of 2 sexes which sometimes differ from each other in a wonderful manner. Doubtful species. The forms which possess in some considerable degree the character of species, but which are so closely similar to other forms, or are so closely linked to them by intermediate gradations, that naturalists do not like to rank them as distinct species, are in several respects the most important for us. We have every reason to believe that many of these doubtful and closely allied forms have permanently retained their characters for a long time; for as long, as far as we know, as have good and true species. Practically, when a naturalist can unite by means of intermediate links any 2 forms, he treats the one as a variety of the other, ranking the most common, but sometimes the one first described as the species, and the other as the variety. But cases of great difficulty, which I will not here enumerate, can sometimes arise in deciding whether or not to rank one form as a variety of another, even when they are closely connected by intermediate links. Nor will the commonly assumed hybrid nature of the intermediate forms always remove the difficulty. In very many cases, however, one form is ranked as a variety of another, not because the intermediate links have actually been found, but because analogy leads the observer to suppose either that they do now somewhere exist, or may formerly have existed, and here a wide door for the entry of doubt and conjecture is opened. Hence, in determining whether a form should be ranked as a species or a variety, the opinion of naturalists having sound judgment and wide experience seems the only guide to follow. We must, however, in many cases, decide by a majority of naturalists, for few well-marked and well-known varieties can be named which have not been ranked as species by at least some competent judges. That varieties of this doubtful nature are far from uncommon cannot be disputed. Compare the several floras of Great Britain, of France, or of the United States, drawn up by different botanists, and see what a surprising number of forms have been ranked by one botanist as good species, and by another as mere varieties. Mr. H.C. Watson, to whom I lie under deep obligation for assistance of all kinds, has marked for me 182 British plants, which are generally considered as varieties, but which have all been ranked by botanists as species, and in making this list he has omitted many trifling varieties, but which nevertheless have been ranked by some botanists as species, and he has entirely omitted several highly polymorphic genera. Under genera, including the most polymorphic forms, Mr. Babington gives 251 species, whereas Mr. Bentham gives only 112, a difference of 139 doubtful forms. Among animals which unite for each birth, and which are highly locomotive, doubtful forms, ranked by one zoologist as a species, and by another as a variety, can rarely be found within the same country, but are common in separated areas. How many of the birds and insects in North America and Europe, which differ very slightly from each other, have been ranked by one eminent naturalist as undoubted species, and by another as varieties, or, as they are often called, geographical races? Mr. Wallace, in several valuable papers on the various animals, especially on the Lepidoptera, inhabiting the islands of the great Malayan archipelago, shows that they may be classed under 4 heads, namely, as variable forms, as local forms, as geographical races or subspecies, and as true representative species. The first or variable forms vary much within the limits of the same island. The local forms are moderately constant and distinct in each separate island. But when all from the several islands are compared together, the differences are seen to be so slight and graduated that it is impossible to define or describe them, though at the same time the extreme forms are sufficiently distinct. The geographical races or subspecies are local forms completely fixed and isolated, but as they do not differ from each other by strongly marked and important characters, there is no possible test but individual opinion to determine which of them shall be considered as species and which as varieties. Lastly, representative species fill the same place in the natural economy of each island, as do the local forms and subspecies, but, as they are distinguished from each other by a greater amount of difference than that between the local forms and subspecies, they are almost universally ranked by naturalists as true species. Nevertheless, no certain criterion can possibly be given by which variable forms, local forms, subspecies, and representative species can be recognized. Many years ago, when comparing and seeing others compare the birds from the closely neighbouring islands of the Galapagos archipelago, one with another, and with those from the American mainland, I was much struck how entirely vague and arbitrary is the distinction between species and varieties. On the islets of the little Madeira group there are many insects which are characterized as varieties in Mr. Wollaston's admirable work, but which would certainly be ranked as distinct species by many entomologists. Even Ireland has a few animals, now generally regarded as varieties, but which have been ranked as species by some zoologists. Several experienced ornithologists consider our British red grouse as only a strongly marked race of a Norwegian species, whereas the greater number rank it as an undoubted species peculiar to Great Britain. A wide distance between the homes of two doubtful forms leads many naturalists to rank them as distinct species. But what distance, it has been well asked, will suffice? If that between America and Europe is ample, will that between Europe and the Azores, or Madeira, or the Canaries, or between the several islets of these small archipelagos, be sufficient? Mr. B.D. Walsh, a distinguished entomologist of the United States, has described what he calls phyto-phagic varieties and phyto-phagic species. Most vegetable-feeding insects live on one kind of plant, or on one group of plants. Some feed indiscriminately on many kinds, but do not in consequence vary. In several cases, however, insects found living on different plants have been observed by Mr. Walsh to present in their larval or mature state, or in both states, slight, though constant differences in colour, size, or in the nature of their secretions. In some instances the males alone, in other instances both males and females, have been observed thus to differ in a slight degree. When the differences are rather more strongly marked, and when both sexes and all ages are affected, the forms are ranked by all entomologists as good species. But no observer can determine for another, even if he can do so for himself, which of these phytophagic forms ought to be called species and which varieties. Mr. Walsh ranks the forms which it may be supposed would freely intercross as varieties, and those which appear to have lost this power as species. As the differences depend on the insects having long fed on distinct plants, it cannot be expected that intermediate links connecting the several forms should now be found. The naturalist thus loses his best guide in determining whether to rank doubtful forms as varieties or species. This likewise necessarily occurs with closely allied organisms which inhabit distinct continents or islands. When, on the other hand, an animal or plant ranges over the same continent, or inhabits many islands in the same archipelago, and presents different forms in the different areas, there is always a good chance that intermediate forms will be discovered which will link together the extreme states, and these are then degraded to the rank of varieties. Some few naturalists maintain that animals never present varieties, but then these same naturalists rank the slightest difference as of specific value, and when the same identical form is met with in two distant countries, or in two geological formations, they believe that two distinct species are hidden under the same dress. The term species thus comes to be a mere useless abstraction, implying and assuming a separate act of creation. It is certain that many forms, considered by highly competent judges to be varieties, resemble species so completely in character that they have been thus ranked by other highly competent judges. But to discuss whether they ought to be called species or varieties, before any definition of these terms has been generally accepted, is vainly to beat the air. Many of the cases of strongly marked varieties or doubtful species well deserve consideration, for several interesting lines of argument, from geographical distribution, analogical variation, hybridism, etc., have been brought to bear in the attempt to determine their rank, but space does not here permit me to discuss them. Close investigation, in many cases, will no doubt bring naturalists to agree how to rank doubtful forms. Yet it must be confessed that it is in the best known countries that we find the greatest number of them. I have been struck with the fact that if any animal or plant in a state of nature be highly useful to man, or from any cause closely attracts his attention, varieties of it will almost universally be found recorded. These varieties, moreover, will often be ranked by some authors as species. Look at the common oak, how closely it has been studied, yet a German author makes more than a dozen species out of forms which are almost universally considered by other botanists to be varieties. And in this country the highest botanical authorities and practical men can be quoted to show that the sessile and pedunculated oaks are either good and distinct species, or mere varieties. I may here allude to a remarkable memoir lately published by A. de Candolle on the oaks of the whole world. No one ever had more ample materials for the discrimination of the species, or could have worked on them with more zeal and sagacity. He first gives in detail all the many points of structure which vary in the several species, and estimates numerically the relative frequency of the variations. He specifies above a dozen characters which may be found varying even on the same branch, sometimes according to age or development, sometimes without any assignable reason. Such characters are not of course of specific value, but they are, as Asa Gray has remarked in commenting on this memoir, such as generally enter into specific definitions. De Candolle then goes on to say that he gives the rank of species to the forms that differ by characters never varying on the same tree, and never found connected by intermediate states. After this discussion, the result of so much labour, he emphatically remarks, "They are mistaken who repeat that the greater part of our species are clearly limited, and that the doubtful species are in a feeble minority." This seemed to be true, so long as a genus was imperfectly known, and its species were founded upon a few specimens, that is to say, were provisional. Just as we come to know them better, intermediate forms flow in, and doubts as to specific limits augment. He also adds that it is the best known species which present the greatest number of spontaneous varieties and subvarieties. Thus, Quercus robur has 28 varieties, all of which, excepting 6, are clustered round 3 subspecies, namely Q. pedunculata, sessiliflora, and pubescens. The forms which connect these 3 subspecies are comparatively rare, and, as Asa Gray again remarks, if these connecting forms which are now rare were to become totally extinct, the 3 subspecies would hold exactly the same relation to each other as do the 4 or 5 provisionally admitted species which closely surround the typical Quercus robur. Finally, De Candolle admits that out of the 300 species, which will be enumerated in his Prodromus as belonging to the oak family, at least 2/3 are provisional species, that is, are not known strictly to fulfill the definition above given of a true species. It should be added that De Candolle no longer believes that species are immutable creations, but concludes that the derivative theory is the most natural one, and the most accordant with the known facts in paleontology, geographical botany and zoology, of anatomical structure and classification. When a young naturalist commences the study of a group of organisms quite unknown to him, he is at first much perplexed in determining what differences to consider as specific, and what as varietal, for he knows nothing of the amount and kind of variation to which the group is subject, and this shows, at least, how very generally there is some variation. But if he confines his attention to one class within one country, he will soon make up his mind how to rank most of the doubtful forms. His general tendency will be to make many species, for he will become impressed, just like the pigeon or poultry fancier before alluded to, with the amount of difference in the forms which he is continually studying; and he has little general knowledge of analogical variation in other groups, and in other countries, by which to correct his first impressions. As he extends the range of his observations, he will meet with more cases of difficulty, for he will encounter a greater number of closely allied forms. But if his observations be widely extended, he will in the end generally be able to make up his own mind, but he will succeed in this at the expense of admitting much variation, and the truth of this admission will often be disputed by other naturalists. When he comes to study allied forms brought from countries not now continuous, in which case he cannot hope to find intermediate links, he will be compelled to trust almost entirely to analogy, and his difficulties will rise to a climax. Certainly no clear line of demarcation has as yet been drawn between species and subspecies, that is, the forms which in the opinion of some naturalists come very near to, but do not quite arrive at, the rank of species, or, again, between subspecies and well-marked varieties, or between lesser varieties and individual differences. These differences blend into each other by an insensible series, and a series impresses the mind with the idea of an actual passage. Hence I look at individual differences, though of small interest to the systematist, as of the highest importance for us, as being the first step towards such slight varieties as are barely thought worth recording in works on natural history. And I look at varieties which are in any degree more distinct and permanent, as steps toward more strongly marked and permanent varieties, and at the latter as leading to subspecies, and then to species. The passage from one stage of difference to another may, in many cases, be the simple result of the nature of the organism and of the different physical conditions to which it has long been exposed; but with respect to the more important and adaptive characters, the passage from one stage of difference to another may be safely attributed to the cumulative action of natural selection, hereafter to be explained, and to the effects of the increased use or disuse of parts. A well-marked variety may therefore be called an incipient species, but whether this belief is justifiable must be judged by the weight of the various facts and considerations to be given throughout this work. It need not be supposed that all varieties or incipient species attain the rank of species. They may become extinct, or they may endure as varieties for very long periods, as has been shown to be the case by Mr. Wollaston with the varieties of certain fossil land shells in Madeira, and with plants by Gaston de Saporta. If a variety were to flourish so as to exceed in numbers the parent species, it would then rank as the species, and the species as the variety; or it might come to supplant and exterminate the parent species; or both might coexist, and both rank as independent species. But we shall hereafter return to this subject. From these remarks it will be seen that I look at the term species as one arbitrarily given, for the sake of convenience, to a set of individuals closely resembling each other, and that it does not essentially differ from the term variety, which is given to less distinct and more fluctuating forms. The term variety, again, in comparison with mere individual differences, is also applied arbitrarily, for convenience' sake. Wide-ranging, much diffused, and common species vary most. Guided by theoretical considerations, I thought that some interesting results might be obtained in regard to the nature and relations of the species which vary most, by tabulating all the varieties in several well-worked floras. At first this seemed a simple task, but Mr. H.C. Watson, to whom I am much indebted for valuable advice and assistance on this subject, soon convinced me that there were many difficulties, as did subsequently Dr. Hooker, even in stronger terms. I shall reserve for a future work the discussion of these difficulties, and the tables of the proportional numbers of the varying species. Dr. Hooker permits me to add that after having carefully read my manuscript and examined the tables, he thinks that the following statements are fairly well established. The whole subject, however, treated as it necessarily here is with much brevity, is rather perplexing, and allusions cannot be avoided to the struggle for existence, divergence of character, and other questions, hereafter to be discussed. Alphonse de Candolle and others have shown that plants which have very wide ranges generally present varieties, and this might have been expected, as they are exposed to diverse physical conditions, and as they come into competition, which, as we shall hereafter see, is a far more important circumstance, with different sets of organic beings. But my tables further show that, in any limited country, the species which are the most common, that is, abound most in individuals, and the species which are most widely diffused within their own country, and this is a different consideration from wide range, and to a certain extent from commonness, oftenest give rise to varieties sufficiently well marked to have been recorded in botanical works. Hence it is the most flourishing, or, as they may be called, the dominant species, those which range widely, are the most diffused in their own country, and are the most numerous in individuals, which oftenest produce well-marked varieties, or, as I consider them, incipient species. And this, perhaps, might have been anticipated, for, as varieties, in order to become in any degree permanent, necessarily have to struggle with the other inhabitants of the country, the species which are already dominant will be the most likely to yield offspring, which, though in some slight degree modified, still inherit those advantages that enabled their parents to become dominant over their compatriots. In these remarks on predominance, it should be understood that reference is made only to the forms which come into competition with each other, and more especially to the members of the same genus or class having nearly similar habits of life. With respect to the number of individuals or commonness of species, the comparison of course relates only to the members of the same group. One of the higher plants may be said to be dominant if it be more numerous in individuals and more widely diffused than the other plants of the same country, which live under nearly the same conditions. A plant of this kind is not the less dominant because some conferva inhabiting the water, or some parasitic fungus is infinitely more numerous in individuals and more widely diffused. But if the conferva or parasitic fungus exceeds its allies in the above respects, it will then be dominant within its own class. Species of the larger genera in each country vary more frequently than the species of the smaller genera. If the plants inhabiting a country, as described in any flora, be divided into two equal masses, all those in the larger genera, i.e., those including many species, being placed on one side, and all those in the smaller genera on the other side, the former will be found to include a somewhat larger number of the very common and much diffused or dominant species. This might have been anticipated, for the mere fact of many species of the same genus inhabiting any country shows that there is something in the organic or inorganic conditions of that country favourable to the genus, and consequently we might have expected to have found in the larger genera, or those including many species, a larger proportional number of dominant species. But so many causes tend to obscure this result, that I am surprised that my tables show even a small majority on the side of the larger genera. I will here allude to only two causes of obscurity. Fresh water and salt-loving plants generally have very wide ranges, and are much diffused, but this seems to be connected with the nature of the stations inhabited by them, and has little or no relation to the size of the genera to which the species belong. Again, plants low in the scale of organisation are generally much more widely diffused than plants higher in the scale, and here again there is no close relation to the size of the genera. The cause of lowly organised plants ranging widely will be discussed in our chapter on Geographical distribution. From looking at species as only strongly marked and well-defined varieties, I was led to anticipate that the species of the larger genera in each country would oftener present varieties than the species of the smaller genera. For wherever many closely related species, i.e., species of the same genus, have been formed, many varieties or incipient species ought, as a general rule, to be now forming. Where many large trees grow, we expect to find saplings. Where many species of a genus have been formed through variation, circumstances have been favourable for variation, and hence we might expect that the circumstances would generally still be favourable to variation. On the other hand, if we look at each species as a special act of creation, there is no apparent reason why more varieties should occur in a group having many species than in one having few. To test the truth of this anticipation, I have arranged the plants of 12 countries, and the coleopterous insects of 2 districts, into 2 nearly equal masses, the species of the larger genera on one side, and those of the smaller genera on the other side, and it has invariably proved to be the case that a larger proportion of the species on the side of the larger genera presented varieties, than on the side of the smaller genera. Moreover, the species of the larger genera which present any varieties invariably present a larger average number of varieties than do the species of the small genera. Both these results follow when another division is made, and when all the least genera, with from only 1 to 4 species, are altogether excluded from the tables. These facts are of plain signification on the view that species are only strongly marked and permanent varieties, for wherever many species of the same genus have been formed, or where, if we may use the expression, the manufactory of species has been active, we ought generally to find the manufactory still in action, more especially as we have every reason to believe the process of manufacturing new species to be a slow one. And this certainly holds true if varieties be looked at as incipient species, for my tables clearly show, as a general rule, that wherever many species of a genus have been formed, the species of that genus present a number of varieties, that is, of incipient species, beyond the average. It is not that all large genera are now varying much, and are thus increasing in the number of their species, or that no small genera are now varying and increasing; for if this had been so, it would have been fatal to my theory, inasmuch as geology plainly tells us that small genera have in the lapse of time often increased greatly in size, and that large genera have often come to their maxima, declined, and disappeared. All that we want to show is, that where many species of a genus have been formed, on an average many are still forming, and this certainly holds good. Many of the species included within the larger genera resemble varieties in being very closely, but unequally, related to each other, and in having restricted ranges. There are other relations between the species of large genera and their recorded varieties, which deserve notice. We have seen that there is no infallible criterion by which to distinguish species and well-marked varieties, and when intermediate links have not been found between doubtful forms, naturalists are compelled to come to a determination by the amount of difference between them, judging by analogy whether or not the amount suffices to raise one or both to the rank of species. Hence the amount of difference is one very important criterion in settling whether two forms should be ranked as species or varieties. Now, Fries has remarked in regard to plants, and Westwood in regard to insects, that in large genera the amount of difference between the species is often exceedingly small. I have endeavoured to test this numerically by averages, and, as far as my imperfect results go, they confirm the view. I have also consulted some sagacious and experienced observers, and, after deliberation, they concur in this view. In this respect, therefore, the species of the larger genera resemble varieties more than do the species of the smaller genera. Or, the case may be put in another way, and it may be said that in the larger genera, in which a number of varieties or incipient species greater than the average are now manufacturing, many of the species already manufactured still to a certain extent resemble varieties, for they differ from each other by a less than the usual amount of difference. Moreover, the species of the larger genera are related to each other in the same manner as the varieties of any one species are related to each other. No naturalist pretends that all the species of a genus are equally distinct from each other; they may generally be divided into subgenera, or sections, or lesser groups. As Fries has well remarked, little groups of species are generally clustered like satellites around other species. And what are varieties but groups of forms, unequally related to each other, and clustered round certain forms, that is, round their parent species? Undoubtedly there is one most important point of difference between varieties and species, namely, that the amount of difference between varieties, when compared with each other or with their parent species, is much less than that between the species of the same genus. But when we come to discuss the principle, as I call it, of divergence of character, we shall see how this may be explained, and how the lesser differences between varieties tend to increase into the greater differences between species. There is one other point which is worth notice. Varieties generally have much restricted ranges. This statement is indeed scarcely more than a truism, for if a variety were found to have a wider range than that of its supposed parent species, their denominations would be reversed. But there is reason to believe that the species which are very closely allied to other species, and in so far resemble varieties, often have much restricted ranges. For instance, Mr. H. C. Watson has marked for me in the well-sifted London Catalogue of Plants, 4th edition, 63 plants which are therein ranked as species, but which he considers as so closely allied to other species as to be of doubtful value. These 63 reputed species range on an average over 6.9 of the provinces into which Mr. Watson has divided Great Britain. Now, in this same catalogue, 53 acknowledged varieties are recorded, and these range over 7.7 provinces, whereas the species to which these varieties belong range over 14.3 provinces. So that the acknowledged varieties have very nearly the same restricted average range, as have the closely allied forms, marked for me by Mr. Watson as doubtful species, but which are almost universally ranked by British botanists as good and true species. Summary. Finally, varieties cannot be distinguished from species, except, first, by the discovery of intermediate linking forms, and, secondly, by a certain indefinite amount of difference between them. For two forms, if differing very little, are generally ranked as varieties, notwithstanding that they cannot be closely connected, but the amount of difference considered necessary to give to any two forms the rank of species cannot be defined. In genera having more than the average number of species in any country, the species of these genera have more than the average number of varieties. In large genera the species are apt to be closely but unequally allied together, forming little clusters round other species. Species very closely allied to other species apparently have restricted ranges. In all these respects, the species of large genera present a strong analogy with varieties. And we can clearly understand these analogies if species once existed as varieties and thus originated, whereas these analogies are utterly inexplicable if species are independent creations. We have also seen that it is the most flourishing or dominant species of the larger genera within each class, which on an average yield the greatest number of varieties, and varieties, as we shall hereafter see, tend to become converted into new and distinct species. Thus the larger genera tend to become larger, and throughout nature the forms of life which are now dominant tend to become still more dominant, by leaving many modified and dominant descendants. But, by steps hereafter to be explained, the larger genera also tend to break up into smaller genera. And thus the forms of life throughout the universe become divided into groups subordinate to groups. End of chapter 2. Read by Kara Schallenberg on February 9th, 2006, in Oceanside, California.
Origin of the Species by Means of Natural Selection, 6th edition. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Chapter 3. The Struggle for Existence. Its bearing on natural selection, the term used in a wide sense, geometrical ratio of increase, rapid increase of naturalized animals and plants, nature of the checks to increase, competition universal, effects of climate, protection from the number of individuals, complex relations of all animals and plants throughout nature, struggle for life most severe between individuals and varieties of the same species, often severe between species of the same genus, the relation of organism to organism, the most important of all relations. Before entering on the subject of this chapter, I must make a few preliminary remarks on how the struggle for existence bears on natural selection. It has been seen in the last chapter that among organic beings in a state of nature there is some individual variability. Indeed, I am not aware that this has ever been disputed. It is immaterial for us whether a multitude of doubtful forms be called species or subspecies or varieties, what rank, for instance, the 200 or 300 doubtful forms of British plants are entitled to hold, if the existence of any well-marked varieties be admitted. But the mere existence of individual variability, and of some few well-marked varieties, though necessary as the foundation for the work, helps us but little in understanding how species arise in nature. How have all those exquisite adaptations of one part of the organization to another part, and to the conditions of life, and of one organic being to another being, been perfected? We see these beautiful co-adaptations most plainly in the woodpecker and the mistletoe, and only a little less plainly in the humblest parasite which clings to the hairs of a quadruped or feathers of a bird, in the structure of the beetle which drives through the water, in the plumed seed which is wafted by the gentlest breeze. In short, we see beautiful adaptations everywhere and in every part of the organic world. Again, it may be asked, how is it that varieties, which I have called incipient species, become ultimately converted into good and distinct species, which in most cases obviously differ from each other far more than do the varieties of the same species? How do those groups of species which constitute what are called distinct genera, and which differ from each other more than do the species of the same genus, arise? All these results, as we shall more fully see in the next chapter, follow from the struggle for life. Owing to this struggle, variations, however slight, and from whatever cause proceeding, if they may be in any degree profitable to the individuals of a species, in their infinitely complex relations to other organic beings, and to their physical conditions of life, will tend to the preservation of such individuals, and will generally be inherited by the offspring. The offspring also will thus have a better chance of surviving, for, of the many individuals of any species which are periodically born, but a small number can survive. I have called this principle, by which each slight variation, if useful, is preserved, by the term natural selection, in order to mark its relation to man's power of selection. But the expression is often used by Mr. Herbert Spencer, of the survival of the fittest, is more accurate, and is sometimes equally convenient. We have seen that man by selection can certainly produce great results, and can adapt organic beings to his own uses, through the accumulation of slight but useful variations given to him by the hand of nature. But natural selection, we shall hereafter see, is a power incessantly ready for action, and is as immeasurably superior to man's feeble efforts as the work of nature are to those of art. We will now discuss in a little more detail the struggle for existence. In my future work this subject will be treated, as it well deserves, at greater length. The elder de Candolle and Lyell have largely and philosophically shown that all organic beings are exposed to severe competition. In regard to plants, no one has treated this subject with more spirit and ability than W. Herbert, Dean of Manchester, evidently the result of his great horticultural knowledge. Nothing is easier than to admit in words the truth of the universal struggle for life, or more difficult, at least I found it so, than constantly to bear this conclusion in mind. Yet unless it be thoroughly ingrained in the mind, the whole economy of nature, with every fact on distribution, rarity, abundance, extinction, and variation, will be dimly seen or quite misunderstood. We behold the face of nature bright with gladness. We often see superabundance of food. We do not see, or we forget, that the birds which are idly singing round us mostly live on insects or seeds, and are thus constantly destroying life. Or we forget how largely these songsters, or their eggs, or their nestlings, are destroyed by birds and beasts of prey. We do not always bear in mind that though food may be now superabundant, it is not so at all seasons of each recurring year. The term struggle for existence, used in a large sense. I should premise that I use this term in a large and metaphorical sense, including independence of one being on another, and including, which is more important, not only the life of the individual, but success in leaving progeny. Two canine animals, in a time of death, may be truly said to struggle with each other which shall get food and live. But a plant on the edge of a desert is said to struggle for life against drought, though more properly it should be said to be dependent on the moisture. A plant which annually produces 1,000 seeds, of which only one of an average comes to maturity, may be more truly said to struggle with the plants of the same kind and other kinds which are already clothing the ground. The mistletoe is dependent on the apple and a few other trees, but can only in a far-fetched sense be said to struggle with these trees, for if too many of these parasites grow on the same tree, it languishes and dies. But several seedling mistletoes, growing close together on the same branch, may more truly be said to struggle with each other. As the mistletoe is disseminated by birds, its existence depends on them, and it may metaphorically be said to struggle with other fruit-bearing plants, in tempting the birds to devour and thus disseminate its seed. In these several senses which pass into each other, I use for convenience' sake the general term struggle for existence. Geometrical ratio of increase. A struggle for existence inevitably follows from the high rate at which all organic beings tend to increase. Every being which during its natural lifetime produces several eggs or seeds must suffer destruction during the same period of its life, and during some season or occasional year. Otherwise, on the principle of geometrical increase, its numbers would quickly become so inordinately great that no country could support the product. Hence, as more individuals are produced than can possibly survive, there must in every case be a struggle for existence, either one individual with another of the same species, or with the individuals of distinct species, or with the physical conditions of life. It is the doctrine of Malthus applied with manifold force to the whole animal and vegetable kingdoms, for in this case there can be no artificial increase of food and no prudential restraint from marriage. Although some species may be now increasing more or less rapidly in numbers, all cannot do so, for the world would not hold them. There is no exception to the rule that every organic being naturally increases at so high a rate, that, if not destroyed, the earth would soon be covered by the progeny of a single pair. Even slow-breeding man has doubled in 25 years, and at this rate, in less than 1,000 years, there would literally not be standing room for this progeny. Linnaeus has calculated that if an annual plant produced only 2 seeds, and there is no plant so unproductive as this, and their seedlings next year produced 2, and so on, then in 20 years there would be 1,000,000 plants. The elephant is reckoned the slowest breeder of all known animals, and I have taken some pains to estimate its probable minimum rate of natural increase. It will be safest to assume that it begins breeding when 30 years old, and goes on breeding till 90 years old, bringing forth 6 young in the interval, and surviving till 100 years old. If this be so, after a period from 740 to 750 years, there would be nearly 19,000,000 elephants alive descended from the first pair. But we have better evidence on this subject than mere theoretical calculations, namely the numerous recorded cases of the astonishingly rapid increase of various animals in a state of nature, when circumstances have been favourable to them during 2 or 3 following seasons. Still more striking is the evidence from our domestic animals of many kinds which have run wild in several parts of the world. If the statements of the rate of increase of slow-breeding cattle and horses in South America, and latterly Australia, had not been well authenticated, they would have been incredible. So it is with plants. Cases could be given of introduced plants which have become common throughout whole islands in a period of less than 10 years. Several of the plants, such as the cardoon and tall thistle, which are now the commonest over the wide plains of La Plata, clothing square leagues of surface almost to the exclusion of every other plant, have been introduced from Europe. And there are plants which now range in India, as I hear from Dr. Falconer, from Cape Comorin, to the Himalaya, which have been imported from America since its discovery. In such cases, and endless others could be given, no one supposes that the fertility of the animals or plants has been suddenly and temporarily increased in any sensible degree. The obvious explanation is that the conditions of life have been highly favourable, and that there has consequently been less destruction of the old and young, and that nearly all the young have been enabled to breed. Their geometrical ratio of increase, the result of which never fails to be surprising, simply explains their extraordinarily rapid increase and wide diffusion in their new homes. In a state of nature, almost every full-grown plant annually produces seed, and among animals there are very few which do not annually pair. Hence we may confidently assert that all plants and animals are tending to increase at a geometrical ratio, that all would rapidly stock every station in which they could anyhow exist, and that this geometrical tendency to increase must be checked by destruction at some period of life. Our familiarity with the larger domestic animals tends, I think, to mislead us. We see no great destruction falling on them, and we do not keep in mind that thousands are annually slaughtered for food, and that in a state of nature an equal number would have somehow to be disposed of. The only difference between organisms which annually produce eggs or seeds by the thousand and those which produce extremely few is that the slow breeders would require a few more years to people, under favourable conditions, a whole district, let it be ever so large. The condor lays a couple of eggs and the ostrich a score, and yet in the same country the condor may be the most numerous of the two. The fulmar petrel lays but one egg, yet is believed to be the most numerous bird in the world. One fly deposits hundreds of eggs, and another, like the hippobosca, a single one. But this difference does not determine how many individuals of the two species can be supported in a district. A large number of eggs is of some importance to those species which depend on a fluctuating amount of food, for it allows them to rapidly increase in number. But the real importance of a large number of eggs or seeds is to make up for much destruction at some period of life, and this period in the great majority of cases is an early one. If an animal can in any way protect its own eggs or young, a small number may be produced, and yet the average stock be fully kept up. But if many eggs or young are destroyed, many must be produced, or the species will become extinct. It would suffice to keep up the full number of a tree which lived on average for 1,000 years, if a single seed were produced once in 1,000 years, supposing that this seed were never destroyed and could be ensured to germinate in a fitting place. So that in all cases the average number of any animal or plant depends only indirectly on the number of its eggs or seeds. In looking at nature it is most necessary to keep the foregoing considerations always in mind, never to forget that every single organic being may be said to be striving to the utmost to increase their numbers, that each lives by a struggle at some period of its life, that heavy destruction inevitably falls either on the young or old, during each generation or at recurrent intervals. Lighten any check, mitigate the destruction ever so little, and the number of the species will almost instantaneously increase to any amount. Nature of the checks to increase. The causes which check the natural tendency of each species to increase are most obscure. Look at the most vigorous species. By as much as it swarms in numbers, by so much it will tend to increase still further. We know not exactly what the checks are in a single instance, nor will this surprise any one who reflects on how ignorant we are on this head, even in regard to mankind, although so incomparably better known than any other animal. This subject of the checks to increase has been ably treated by several authors, and I hope in a future work to discuss it at considerable length, more especially in regard to the feral animals of South America. Here I will make only a few remarks, just to recall the reader's mind some of the chief points. Eggs, or very young animals, seem generally to suffer most, but this is not invariably the case. With plants, there is a vast destruction of seeds, but from some observations which I have made it appears that the seedlings suffer most from germinating in ground already thickly stocked with other plants. Seedlings also are destroyed in vast numbers by various enemies. For instance, on a piece of ground 3 feet long and 2 wide, dug and cleared, where there could be no choking from other plants, I marked all the seedlings of our native weeds as they came up, and out of 357, no less than 295 were destroyed, chiefly by slugs and insects. If turf, which has long been mown, and the case would be the same with turf closely browsed by quadrupeds, be let to grow, the more vigorous plants gradually kill the less vigorous, though fully grown plants. Thus, out of 20 species grown on a little plot of mown turf, 3 feet by 4, 9 species perished, from the other species being allowed to grow up freely. The amount of food for each species, of course, gives the extreme limit to which each can increase. But very frequently it is not the obtaining food, but the serving as prey to other animals, which determines the average number of a species. Thus there seems to be little doubt that the stock of partridges, grouse, and hares on any large estate depends chiefly on the destruction of vermin. If not one head of game were shot during the next 20 years in England, and, at the same time, if no vermin were destroyed, there would, in all probability, be less game than at present, although hundreds of thousands of game animals are now annually shot. On the other hand, in some cases, as with the elephant, none are destroyed by beasts of prey, for even the tiger in India most rarely dares to attack a young elephant protected by its dam. Climate plays an important part in determining the average numbers of a species, and periodical seasons of extreme cold or drought seem to be the most effective of all checks. I estimated, chiefly from the greatly reduced numbers of nests in the spring, that the winter of 1854-55 destroyed 4/5 of the birds in my own grounds, and this is a tremendous destruction when we remember that 10% is an extraordinarily severe mortality from epidemics with man. The action of climate seems at first sight to be quite independent of the struggle for existence, but in so far as climate chiefly acts in reducing food, it brings on the most severe struggle between the individuals, whether of the same district species, which subsist on the same kind of food. Even when climate, for instance, extreme cold, acts directly, it will be the least vigorous individuals, or those which have got least food through the advancing winter, which will suffer the most. When we travel from south to north, or from a damp region to a dry, we invariably see some species gradually getting rarer, and finally disappearing. And the change of climate being conspicuous, we are tempted to attribute the whole effect to its direct action. But this is a false view. We forget that each species, even where it most abounds, is constantly suffering enormous destruction at some period of its life, from enemies or from competitors for the same place and food. And if these enemies or competitors be in the least degree favored by any slight change of climate, they will increase in numbers. And as each area is already fully stocked with inhabitants, the other species must decrease. When we travel southward and see a species decreasing in numbers, we may feel sure that the cause lies quite as much in other species being favored as in this one being hurt. So it is when we travel northward, but in a somewhat lesser degree, for the number of species of all kinds, and therefore of competitors, decreases northwards. Hence, in going northward, or in ascending a mountain, we far oftener meet with stunted forms, due to the directly injurious action of climate, than we do in proceeding southward, or in descending a mountain. When we reach the Arctic regions, or snow-capped summits, or absolute deserts, the struggle for life is almost exclusively with the elements. That climate acts in main part indirectly by favoring other species, we clearly see in the prodigious number of plants which in our gardens can perfectly well endure our climate, but which never become naturalized, for they cannot compete with our native plants nor resist destruction by our native animals. When a species, owing to highly favorable circumstances, increases inordinately in numbers in a small tract, epidemics, at least this seems generally to occur with our game animals, often ensue. And here we have a limiting check, independent of the struggle for life. But even some of these so-called epidemics appear to be due to parasitic worms, which have from some cause, possibly in part through facility of diffusion among the crowded animals, been disproportionately favoured, and here comes in a sort of struggle between the parasite and its prey. On the other hand, in many cases a large stock of individuals of the same species, relatively to the numbers of its enemies, is absolutely necessary for its preservation. Thus we can easily raise plenty of corn and rapeseed, etc., in our fields, because the seeds are in great excess compared with the number of birds which feed on them. Nor can the birds, though having a superabundance of food at this one season, increase in number proportionately to the supply of seed, as their numbers are checked during the winter. But anyone who has tried knows how troublesome it is to get seed from a few wheat and other such plants in a garden. I have in this case lost every single seed. This view of the necessity of a large stock of the same species for its preservation explains, I believe, some singular facts in nature, such as that of very rare plants being sometimes extremely abundant in the few spots where they do exist, and that of some social plants being social, that is, abounding in individuals, even on the extreme verge of their range. For in such cases we may believe that a plant could exist only where the conditions of its life were so favourable that many could exist together, and thus save the species from utter destruction. I should add that the good effects of intercrossing and the ill effects of close inbreeding no doubt come into play in many of these cases, but I will not here enlarge on this subject. Complex relations of all animals and plants to each other in the struggle for existence. Many cases are on record showing how complex and unexpected are the checks and relations between organic beings which have to struggle together in the same country. I will give only a single instance which, though a simple one, interested me. In Staffordshire, on the estate of a relation, where I had ample means of investigation, there was a large and extremely barren heath, which had never been touched by the hand of man. But several hundred acres of exactly the same nature had been enclosed 25 years previously and planted with Scotch fir. The change in the native vegetation of the planted part of the heath was most remarkable, more than is generally seen in passing from one quite different soil to another. Not only the proportional numbers of the heath plants were wholly changed, but 12 species of plants, not counting grasses and carices, flourished in the plantations, which could not be found in the heath. The effect on the insects must have been still greater, for 6 insectivorous birds were very common in the plantations which were not to be seen on the heath, and the heath was frequented by 2 or 3 distinct insectivorous birds. Here we see how potent has been the effect of the introduction of a single tree, nothing whatever else having been done, with the exception of the land having been enclosed, so that cattle could not enter. But how important an element enclosure is, I plainly saw near Farnham in Surrey. Here there are extensive heaths, with a few clumps of old Scotch firs on the distant hilltops. Within the last 10 years large spaces have been enclosed, and self-sown firs are now springing up in multitudes, so close together that all cannot live. When I ascertained that these young trees had not been sown or planted, I was so much surprised at their numbers that I went to several points of view, whence I could examine hundreds of acres of the enclosed heath, and literally I could not see a single Scotch fir except the old planted clumps. But on looking closely between the stems of a heath, I found a multitude of seedlings and little trees, which had been perpetually browsed down by the cattle. In 1 square yard, at a point some 100 yards distant from the old clumps, I counted 32 little trees, and one of them, with 26 rings of growth, had, during many years, tried to raise its head above the stems of the heath, and had failed. No wonder that as soon as the land was enclosed it became thickly clothed with vigorously growing young firs. Yet the heath was so extremely barren and so extensive that no one would ever have imagined that cattle would have so closely and effectually searched it for food. Here we see that cattle absolutely determine the existence of the Scotch fir, but in several parts of the world insects determine the existence of cattle. Perhaps Paraguay offers the most curious instance of this, for here neither cattle nor horses nor dogs have ever run wild, though they swarm southward and northward in a feral state; and Azara and Reneger have shown that this is caused by the greater number in Paraguay of a certain fly which lays its eggs in the navels of these animals when first born. The increase of these flies, numerous as they are, must be habitually checked by some means, probably by other parasitic insects. Hence, if certain insectivorous birds were to decrease in Paraguay, the parasitic insects would probably increase, and this would lessen the number of the navel-frequenting flies. Then cattle and horses would become feral, and this would certainly greatly alter, as indeed I have observed in parts of South America, the vegetation. This again would largely affect the insects, and this, as we have just seen in Staffordshire, the insectivorous birds, and so onwards in ever-increasing circles of complexity. Not that under nature the relations will ever be as simple as this. Battle within battle must be continually recurring with varying success, and yet in the long run the forces are so nicely balanced that the face of nature remains for long periods of time uniform, though assuredly the merest trifle would give the victory to one organic being over another. Nevertheless, so profound is our ignorance and so high our presumption that we marvel when we hear of the extinction of an organic being. And as we do not see the cause, we invoke cataclysms to desolate the world, or invent laws on the duration of the forms of life. I am tempted to give one more instance showing how plants and animals, remote in the scale of nature, are bound together by a web of complex relations. I shall hereafter have occasion to show that the exotic Lobelia fulgens is never visited in my garden by insects, and consequently, from its particular structure, never sets a seed. Nearly all our orchidaceous plants absolutely require the visits of insects to remove their pollen masses and thus to fertilize them. I find from experiments that humble-bees are almost indispensable to the fertilization of the heartsease violetricolor, for other bees do not visit this flower. I have also found that the visits of bees are necessary for the fertilizations of some kinds of clover, for instance 20 heads of Dutch clover, Trifolium repens, yielded 2,290 seeds, but 20 other heads, protected from bees, produced not one. Again, 100 heads of red clover, T. pratans, produced 2,700 seeds, but the same number of protected heads produced not a single seed. Humble bees alone visited red clover, as other bees cannot reach the nectar. It has been suggested that moths may fertilize the clovers, but I doubt whether they could do so in the case of the red clover, from their weight not being sufficient to depress the wing petals. Hence we may infer as highly probable that, if the whole genus of humble-bees came extinct or very rare in England, the heartsease and red clover would become very rare or wholly disappear. The number of humble-bees in any district depends in a great measure upon the number of field mice which destroy their combs and nest. And Colonel Newman, who has long attended to the habits of humble-bees, believes that more than 2/3 of them are thus destroyed all over England. Now the number of mice is largely dependent, as everyone knows, on the number of cats. And Colonel Newman says, near villages and small towns I have found the nests of humble-bees more numerous than elsewhere, which I attribute to the number of cats that destroy the mice. Hence it is quite credible that the presence of a feline animal in large numbers in a district might determine, through the intervention first of mice and then of bees, the frequency of certain flowers in that district. In the case of every species, many different checks, acting at different periods of life and during different seasons of the year, probably come into play. Some one check, or some few being generally the most potent, but all will concur in determining the average number, or even the existence of species. In some cases it can be shown that widely different checks act on the same species in different districts. When we look at the plants and bushes clothing an entangled bank, we are tempted to attribute their proportional numbers and kinds to what we call chance. But how false a view is this! Everyone has heard that when an American forest is cut down, a very different vegetation springs up. But it has been observed that ancient Indian ruins in the southern United States, which must formerly have been cleared of trees, now display the same beautiful diversity and proportion of kinds as in the surrounding virgin forests. What a struggle must have gone on during long centuries between several kinds of trees, each annually scattering its seed by the thousand. What war between insect and insect, between insects, snails, and other animals, with birds and beasts of prey, all striving to increase, all feeding on each other, or on the trees, their seeds and seedlings, or on the other plants which first clothe the ground and thus check the growth of trees. Throw up a handful of feathers, and all fall to the ground according to definite laws. But how simple is the problem of where each shall fall compared to that of the action and reaction of the innumerable plants and animals, which have determined in the course of centuries the proportional numbers and kinds of trees now growing on the old Indian ruins. The dependency of one organic being on another, as of parasite on its prey, lies generally between beings remote in the scale of nature. This is likewise sometimes the case with those which may strictly be said to struggle with each other for existence, as in the case of locusts and grass-feeding quadrupeds. But the struggle will almost invariably be most severe between the individuals of the same species, for they frequent the same districts, require the same food, and are exposed to the same dangers. In the case of varieties of the same species the struggle will generally be almost equally severe, and we sometimes see the contest soon decided. For instance, if several varieties of wheat be sown together, and the mixed seed be resown, some of the varieties which best suit the soil or climate, or are naturally the most fertile, will beat the others and so yield more seed, and will consequently, in a few years, supplant the other varieties. To keep up a mixed stock of even such extremely close varieties as the variously colored sweet peas, they must be each year harvested separately, and the seed then mixed in due proportion, otherwise the weaker kinds will steadily decrease in number and disappear. So again with the varieties of sheep. It has been asserted that certain mountain varieties will starve out other mountain varieties, so that they cannot be kept together. The same result has followed from keeping together different varieties of medicinal leech. It may even be doubted whether the varieties of any of our domestic plants or animals have so exactly the same strength, habits, and constitution that the original proportions of a mixed stock, crossing being prevented, could be kept up for half a dozen generations, if they were allowed to struggle together in the same manner as beings in a state of nature, and if the seed or young were not annually preserved in due proportion. Struggle for life most severe between individuals and varieties of the same species. As the species of the same genus usually have, though by no means invariably, much similarity in habits and constitution, and always in structure, the struggle will generally be more severe between them, if they come into competition with each other, than between the species of distinct genera. We see this in the recent extension over parts of the United States of one species of swallow having caused the decrease of another species. The recent increase of the missel thrush in parts of Scotland has caused the decrease of the song thrush. How frequently we hear of one species of rat taking the place of another species under the most different climates. In Russia, the small Asiatic cockroach has everywhere driven before it its great congener. In Australia, the imported hive bee is rapidly exterminating the small, stingless native bee. One species of charlock has been known to supplant another species, and so in other cases. We can dimly see why the competition should be most severe between allied forms, which fill nearly the same place in the economy of nature. But probably in no one case could we precisely say why one species has been victorious over another in the great battle of life. A corollary of the highest importance may be deduced from the foregoing remarks, namely, that the structure of every organic being is related, in the most essential yet often hidden manner, to that of all other organic beings, with which it comes into competition for food or resilience, or from which it has to escape, or on which it preys. This is obvious in the structure of the teeth and talons of the tiger, and in that of the legs and claws of the parasite which clings to the hair of the tiger's body. But in the beautifully plumed seed of the dandelion, and in the flattened and fringed legs of the water beetle, the relation seems at first confined to the elements of air and water. Yet the advantage of the plumed seeds no doubt stands in the closest relation to the land being already thickly clothed with other plants, so that the seed may be widely distributed and fall on unoccupied ground. In the water beetle the structure of its legs, so well adapted for diving, allows it to compete with other aquatic insects, to hunt for its own prey, and to escape serving as prey to other animals. The store of nutriment laid up within the seeds of many plants seem at first sight to have no sort of relation to other plants, but from the strong growth of young plants produced from such seeds, as peas and beans, when sown in the midst of long grass, it may be suspected that the chief use of the nutriment in the seed is to favour the growth of the seedlings, whilst struggling with other plants growing vigorously all around. Look at a plant in the midst of its range. Why does it not double or quadruple its numbers? We know that it can perfectly well withstand a little more heat or cold, dampness or dryness, for elsewhere it ranges into slightly hotter or colder, damper or drier districts. In this case we can clearly see that if we wish in imagination to give the plant the power of increasing in numbers, we should have to give it some advantage over its competitors, or over the animals which prey on it. On the confines of its geographical range, a change of constitution with respect to climate would clearly be an advantage to our plant. But we have reason to believe that only a few plants or animals range so far that they are destroyed exclusively by the rigour of the climate. Not until we reach the extreme confines of life in the Arctic regions, or on the borders of an utter desert, will competition cease. The land may be extremely cold or dry, yet there will be competition between some few species or between the individuals of the same species for the warmest or dampest spots. Hence we can see that when a plant or animal is placed in a new country, among new competitors, the conditions of its life will generally be changed in an essential manner, although the climate may be exactly the same as in its former home. If its average numbers are to increase in its new home, we should have to modify it in a different way to what we should have had to do in its native country, for we should have to give it some advantage over a different set of competitors or enemies. It is good thus to try in imagination to give one species an advantage over another. Probably in no single instance should we know what to do. This ought to convince us of our ignorance on the mutual relations of all organic beings, a conviction necessary as it is difficult to acquire. All that we can do is keep steadily in mind that each organic being is striving to increase in a geometrical ratio, that each, at some period of its life, during some season of the year, during each generation, or at intervals, has to struggle for life and to suffer great destruction. When we reflect on this struggle, we may console ourselves with the full belief that the war of nature is not incessant, that no fear is felt, that death is generally prompt, and that the vigorous, the healthy, and the happy survive and multiply. End of chapter 3.